Hello and welcome to the online MOOC for optical communications. We will discuss today modes in an optical fiber. In the previous module we have discussed how a wave would propagate inside an optical fiber based on the total internal reflection. However, total internal reflection is based mostly on the ideas that we discussed in the previous module were based on geometrical optics, something that is quite okay to understand initially how the wave would propagate, but it does not give you the full picture. For example, if I ask you what pattern of the electric field and the magnetic field would exist inside an optical fiber so that I know where to couple the light into the fiber, then you will not be able to tell me that, or you will have to struggle very hard to tell me that from the geometrical optics techniques that we discussed in the previous module. Therefore, what we will do in this module is to start with Maxwell's equations and solve them for the case of the simplest structure of the optical fiber that we can consider of, and then understand what do we mean by electric field and magnetic field patterns. These electric field and magnetic field patterns, which are the solutions of Maxwell's equations, subject to certain boundary conditions that we are going to impose, are called as modes of an optical fiber. So you might have heard of this term mode in the context of an hollow metallic waveguide, the rectangular waveguides which have modes of TE and TM, or a parallel plate waveguide which has modes TE and TM. Here TE stands for transverse electric and TM stands for transverse magnetic. If you consider a plane wave propagating in free space, that would correspond to transverse electromagnetic mode. Here the pattern of a transverse electromagnetic mode is very simple. You have electric field lines in this way, maybe my fingers are pointing in that way, and the magnetic field lines are all perpendicular to electric field, and this pattern itself is perpendicular to the direction of the propagation. So such a simple pattern of electric field and magnetic field, right, is called a mode. Of course, a free space will support this one, a free space will support multiple modes. Those are the different questions of a mode. In fact, normally when we talk of free space, we don't talk of mode there. But if you consider a parallel plate waveguide, something that would be like this, but extending all the way to to the y direction, maybe this is my x direction, then you will see that there are certain patterns of electric and magnetic fields which we call as modes, and only those patterns can exist in the mode in the guided condition. Okay. So when we say a guided mode inside a wave, what we mean is that a particular pattern of E and H fields which are propagating along the waveguide. For example, if you consider a simple symmetric slab made of some dielectric, so let us say the dielectric has a refractive index of N1 here, and N2 would be the surrounding refractive index, correct? So this you can imagine actually as coming in from a certain parallel plate, like this is the kind of a structure that I am actually looking at. Okay. So this extends all the way to infinity on this side, there is an extension towards infinity on that side as well, and this axis may be considered as the x axis, whereas this axis may be considered as the z axis. So you want the wave to propagate along the z axis, okay, and for this wave, if you solve Maxwell's equation, going back to the things that you know from microwave engineering or electromagnetic theory, you will see that there would be a certain patterns of electric field, which I am drawing only for the electric field. There are certain patterns for magnetic field as well. So there are certain patterns for electric field, maybe that is of this nature, or you might have a wave that would go like that. Maybe my pictures are not very nice, but you get the idea. The first one was a half sine wave, the next one is a full sine wave, and so on, right. So these were the structures that we had seen, and then these patterns were associated with TE or TM modes. For a parallel plate waveguide, we actually called them along with a certain additional index. We said that if n denotes the number of half cycles, then that would be my mode nomenclature. I could equally have chosen the number of minima inside, and that is sometimes done. So if for example n denotes the number of minima, then TE0 would correspond to the fundamental mode wherein there is only maxima at the center and the field never goes to 0. Okay. So, this is just a mode nomenclature, the way you write it is slightly different depending on where you are looking at the literature. So, unfortunately it is not, it is although standardized, there is not highly standardized as we would like to see. In any case, what we have spoken to you about the last 5 minutes is that there exist these patterns of electric field and magnetic field, which will be functions of the coordinate system. For a symmetric slab waveguide, my coordinate systems would be in the Cartesian coordinate system, and the variables, the coordinates would be x, y and z. So, you have electric field as a function of x, y and z, magnetic field also as a function of x, y and z. These fields have to satisfy certain boundary conditions. So, such a thing is called as a mode. For the case of this symmetric slab waveguide, the actual behavior at the edges here will be slightly different. In fact, it would be radically different if we were to say so. If this material was, the plates were made up of metals, perfect metals, then we know from the boundary condition that the tangential electric field component must go to 0 there. However, in case of a dielectric to dielectric interface, the only constraint that we have is that the tangential components must be continuous across the surface. There is nothing like they have to be 0 at the surface, they just have to be continuous across the surface. So, what you see is that although within the guided region or within the region of the slab, you will expect a half sine wave or 1 sine wave, 2 sine waves, 3 sine waves and so on, multiple higher order modes. At the edge where these plates are getting, where you are meeting, the field does not really go to 0 there, but rather it extends into the region surrounding the guided region, right. So, if we call this guided region as core and the surrounding region as clad, okay, this is called a symmetric slab waveguide because N2 is the same for surrounding the region N1. Okay. This need not be just an optical fiber. In fact, this waveguide is actually an integrated optical waveguide circuit. Okay. So, in integrated optical device such as a laser or a photodetector or a waveguide, you would see these waveguide modulators, you would see all these type of waveguides. Okay. So, if you look at the field behavior in the core, they would mostly resemble this red and the green curves, which stand for half sine wave or a full sine wave, half sine wave being the fundamental mode, full sine wave being the next higher order mode or the next mode. Okay. At the edge, however, the fields are not really going to 0, but they actually extend or rather decay exponentially. Okay. So, they decay exponentially, and it is our job to match the exponential decay outside that is happening, So, at this point there is an exponential decay, right, and to the field which would be there inside the core. So, the way I have written, clearly these are not meeting because at this junction there is a jump or the asymmetry. So, I have to tailor one of the function amplitudes such that I get a nice extension. So, this would be the exponential extension, right. So, if you call this one as some b e power minus alpha x, where alpha denotes how quickly it is decaying into the cladding, okay, and if you have this one as some sine k x x, okay, I am assuming still this slab waveguide. So, and the amplitude of this one is some a, then I have to adjust the amplitudes a and b, and this adjustment comes from boundary conditions. Okay. So, boundary conditions simply stitch the behavior of the wave in the core and in the cladding region. Now, is it always possible that I always end up with a guided mode, that is energy confined in the core? Actually no. If you look at our example in the previous module where we were discussing the concept of acceptance angle, we said that for a fiber, right, there exists something called as a acceptance angle. So, within which if your light wave is incident, then this light wave is guaranteed to be guided inside the waveguide. However, if you choose to incident your wave at outside this acceptance angle, then it would simply propagate out into the cladding. So, it will not actually be guided, but rather it escapes into the cladding. However, if the cladding were to be truly infinite in extent, then this would have continued to radiate all the way to infinity, right. The energy would be radiated all the way to infinity. But because the cladding is finite, at some point the cladding diameter has to come in, because it is a finite cladding radius. So what happens is that this mode, once it hits, then kind of reflects back, correct, because this region is outside is a different refractive index, this region is a different refractive index. So when the cladding mode hits the clad radius or the clad boundary, then it simply reflects back. So essentially it gets trapped and propagates in the cladding as what is called as a cladding mode. Okay. What propagates inside the core will of course be core modes, okay, or modes inside a core, and there is actually a coupling between the cladding mode and the core mode. So if by any chance I have excited the cladding modes, then these cladding modes will also propagate along with the core mode, of course at different group velocities, owing to the fact that the refractive indices are different and the propagation constants are different, but nevertheless they will start to exchange some power, okay, which means that the power in the actual core mode will be stripped off into the cladding mode. So you see that there is actually a power loss in the core mode. So for that reason it is necessary not to excite any cladding modes, okay. So you want to always have modes guided by the core, and you want to maximize the power that is contained by the core. One simple way of maximizing this power into the core would be to make the radius of the core as large as possible, right. That way if I am tapping the exponential at some point, I will be tapping the exponential at this point. If my core area has grown so much, then I would be tapping this exponential when it is almost going to 0, right. So this is very small. The problem with increasing the core area is that there is a certain parameter called as V parameter, okay, and it is defined as 2 pi a by lambda square root of n1 square minus n2 square, okay. So this 2 pi a by lambda square root of n1 square minus n2 square, and under the assumption that n1 and n2 are approximately equal, of course this has to be greater than n2, right, n1 corresponding to the core refractive index of the fiber, n2 corresponding to the clad refractive index of the fiber, then this V number can be approximately written as 2 pi a by lambda n1 square root of 2 delta, or this entire thing is nothing but numerical aperture as we saw in the last class. So if I were to increase A, right, so if A increases while keeping the numerical aperture constant and the wavelength also to be a constant, then what happens? V increases. Now it turns out that when V is sufficiently large, then the number of modes that the waveguide will support goes as V square by 2, okay, and what you get is, instead of having one mode propagating, which is what you would ideally want, you would start getting multiple higher order modes. So energy is now being eaten away by multiple core modes, just because I decided to constrain the optical power inside the core as much as possible by making the area large, right. So of course the solution would be to then reduce the numerical aperture. Reducing the numerical aperture would mean making n1 minus n2 difference to be as small as possible, delta to be as small as possible, right. So you will see that these are the trade-offs that one has to come up with when designing a fiber for communication system. For a single mode optical fiber communication system, you want no more than one mode to be propagating inside a fiber. So which means that V has to be constrained to a certain value, certain critical value, and we should not be allowed to increase beyond that. There is one advantage of having cladding modes and the core modes interacting with each other. They are used in realizing what are called as long period gratings, okay, where we intentionally perturb or change the cladding refractive index so as to induce a coupling between cladding and the core modes. And these LPGs are quite widely used as gain equalizers for erbium doped fiber amplifiers. So in most erbium doped fiber amplifiers you will see these LPGs. LPGs also have additional uses which we will not get into at this point of time. So coming back to the summary of what we have done, we have looked at the modes, and we said that a mode is essentially a pattern of electric and magnetic fields which satisfies Maxwell conditions, also satisfies the boundary conditions. We have also seen that modes inside an optical fiber can be guided modes, that is the modes which are in the core and they will be propagating along the axis of the fiber. We have also seen that there could be modes which are radiated in the cladding and actually propagate inside as the cladding modes. There is also another mode called as a leaky mode. A leaky mode happens when the mode is near the cutoff. Okay, we will talk about cutoff slightly later, but when the mode is near the cutoff, right, then the propagation constant for that mode is near cutoff, then the mode does not quite become radiating into the cladding, but it simply exponentially decays into the cladding. Okay, it propagates slightly along the axis, but then while it propagates along the axis, its amplitude starts to decay very rapidly. So these are the leaky modes of the optical fiber. So you can take an example here, something that would illustrate the numbers that are involved. So let us suppose that we have selected V is equal to 26.6. Now this is extremely large number, because the number of modes will be 25 square nearly, which is around 600 something, right. So this is quite a large number that you are looking at. However, this is just for the example sake. Suppose I assume that lambda is 1300 nanometer, and I also assume the core radius to be 25 micron. You again see that these are not the standard single mode fibers, because in the last module we have seen what are the typical properties, what is typical values of A and delta, right. So can you calculate what is the numerical aperture here? I will just solve this example because I know the equation here. V is given by 2 pi A by lambda times numerical aperture. So since all the unknown parameters lambda, V and A are given, I can invert this equation to find out what is the numerical aperture. Numerical aperture is in the numerator, so therefore this must be equal to lambda V divided by 2 pi A. So hopefully that is the correct expression. Yeah, this is the correct expression. Substituting the values here, what you get is a numerical aperture of 0.22. You can see that the numerical aperture is also not small, right. Now let us turn around the problem, and I will leave this as an exercise to you. Assume that for some reason I want V to be 2.405. You will see why so sometime later when we discuss the modes. I fix A to 4.1 micron. Remember, A is the radius. Okay, so I fix A to be 4.1 micron, and I want the wave to be propagating at 1550 nanometer. Okay, so I want the wave to be propagating at 1550 nanometer. Can you calculate what should be the numerical aperture? And if I tell you that N1 is nearly 1.44, can you calculate what should be N2? Okay, so I will leave this as a exercise problem to you. The solution will be supplied after the assignments are handed over to you. Okay, let's also give you one more exercise. Here you are going to design a single mode fiber, as opposed to the earlier problem where NA actually has a particular value because all the parameters are known to you. Let me say my only constraint is that V has to be less than or equal to 2.405, and then lambda should be 1550 nanometer. Okay. So I will say only these two values and ask you to find out the core radius A, find out the numerical aperture. Clearly there is going to be an infinite number of choices in this problem, correct? So there will be an infinite number of choices. See whether you will be able to come up with some numbers. More importantly, I want you to understand what happens with when you change A, when you change numerical aperture. Okay, so I want you to understand that operation. Okay. Finally, after you have selected a particular value of radius and numerical aperture, let us say I make lambda to be 1300 nanometer. Okay, so lambda becomes 1300 nanometer. See for the selected values of A and numerical aperture whether the wave will be guided here when lambda is changed to 1300 nanometer. Okay, this brings up a very important property of cutoff wavelength. Okay, so see if you can do this exercise. We will supply the solutions later after the assignments are handed over to you. Okay, now we need to jump into Maxwell's equations to understand more about what these guided modes are and what kind of a pattern am I going to generate inside the fiber. As I said, it is important for me to know what the pattern is. So if I know that power of the mode that is propagating inside the fiber is 0 at the center, and if I have a lens system which is sending light but the lens is focused at the center of the fiber, then nothing will be excited, because at the center the power that would be guided by the fiber is 0. So there is a mismatch between what the exciting condition is and what is the power condition there. On the other hand, if I know that the power is maximum at the center and I have a lens system which is then focusing light at the center, then this mode can get excited. So if you have to excite a mode, you have to excite the electric field and the magnetic field patterns out there, and you can do that only if you know what is the modal pattern or mode pattern of the modes which are propagating inside the fiber, and that is what we are going to look at. So in the remainder of the module, we will first outline the steps and then give you couple of basic equations. In the next module, we will continue to solve the equations. So how to obtain modes? In a general setting, this would be a very complicated problem because everything can be changing. So that's going to be a very involved problem to solve. Fortunately, we don't need to solve such complicated problems. Even the simple problem that we are solving is already complicated, but we will not introduce additional complexity. So let us spell out what are the assumptions that we are going to make. Assumption number 1, I am going to assume that the core is filled with homogeneous dielectric. Okay. So it is filled with homogeneous dielectric. It is characterized by a single parameter N1, which is the refractive index, and it is completely independent of x, y and z. Okay. It is also independent of the direction of the coordinate system. Therefore, N1 actually is the result of a linear, homogeneous and isotropic medium. Linear, isotropic plus homogeneous dielectric. So you can capture this by saying LIH dielectric. We will also assume that the clad is an LIH medium, okay, characterized by a single parameter N2, and it has a radius which for our purpose, radius B, for our purpose is so large compared to A that you can almost consider this to be infinite. Okay. However, the core has a radius A which is definitely finite. We will assume a single sinusoidal excitation. Because the medium is linear, any complicated waveform or any reasonably complicated waveform can be expressed as sum of sinusoids. So if I know how the mode behaves for a single sinusoidal frequency, then I can put up the solutions, superimpose the solutions of that and use the techniques of Fourier theory to obtain the response to a complicated waveform. So I'll assume the single sinusoidal excitation. So we have spelled out the parameters that we are going to consider. Of course, we know that N1 must be greater than N2 to enable total internal reflection, right. So this is one additional requirement for a single mode optical fiber that we are going to put up for any waveguide that we need to put up, which is dielectric waveguide. If you were to look at the structure itself, this would be the core and that would be the cladding. And if you look at what is the refractive index distribution would look like this. So this is N1 and this is N2. Okay. So the refractive index distribution is N1 and N2, and the difference between N1 and N2 is captured by the numerical aperture. Okay. So the core has a radius of A, the clad has a radius of B which is much larger than A. Alright, what are the steps that are involved? Steps to find the modes. So we will start with writing Maxwell's equations. Okay, Maxwell's equations we are going to write in a given coordinate system. So we will employ a certain coordinate system that is easier for us to solve. So we take this coordinate system and then write Maxwell's equations in that coordinate system. Then what we do, we express the perpendicular components of the electric field and perpendicular components of the magnetic field in terms of the axial components, okay, which we will consider to be Ez and Hz. Okay. The coordinate system that we are going to consider will of course be cylindrical, because this is an optical fiber that we are looking at, and in the cylindrical coordinate system you will have R phi and z, and we assume that the fiber is uniform along the z axis. So this is the z axis and it is uniform along the z axis, by which we mean that if you take a cross section here, it would be a perfect circle. If you take a cross section here, that would also be a perfect circle. Okay, so this is the uniform assumption that we are going to employ. Once you have done part 2, right, you have expressed a perpendicular and h perpendicular in terms of Ez and Hz, you solve equations for Ez and Hz. Most likely you will be solving this equation, what is called as the Helmholtz equation for Ez and Hz. Okay. So you will be solving the Helmholtz equation. Of course, we are assuming single sinusoidal, therefore we will actually be talking about phasors, not the fields which are functions of both z and time. So the time dependence is thrown out by going into the phasor notation. So all these Ez, Hz are phasors. Okay. I hope that you remember what phasors are. Once you have found Ez and Hz, then you apply boundary conditions. Okay. So the result of the equations for corresponding to Ez and Hz, and then apply boundary conditions to evaluate arbitrary constants that are going to come up in the solution. So you have to evaluate those arbitrary constants. Now there might be many constants that are interesting to evaluate, but what you are after is to find this critical parameter known as propagation constant, okay, of the guided mode. You want to know not only how the wave is propagating, but you also need to know what is the propagation constant of the wave. Okay, so that is very important. So what you are after is basically to obtain this critical parameter known as the propagation constant. So that's essentially the objective of applying boundary conditions and deriving the necessary equations. Once you have finished step number 4, the obvious step for 5 would be to go back and substitute this Ez and Hz in the expressions for E perpendicular and H perpendicular, and then obtain those field patterns as well. Okay. E perpendicular and H perpendicular are the electric fields and the magnetic fields which lie in the plane that is perpendicular to the propagation. So this is the direction of the propagation. Let us put it this way. This is the direction of the propagation which is along the z axis. The plane that would be perpendicular to this in the cylindrical coordinate system will be the r and phi plane. Okay. So perpendicular components mean ER, E phi, HR and H phi. In contrast to hollow metallic waveguide, where you can have a situation where Ez is 0, the corresponding modes are called as TE modes, Hz is 0, the corresponding modes are called as TM modes. In this optical fiber, you rarely get such a chance. You actually have, in a very general sense, both electric field the longitudinal component, magnetic field longitudinal component, that is Ez as well as Hz are not 0. However, it might so happen that Ez might be small compared to Hz. In that case, we call this as a HE mode. We might also have another situation where Ez is larger compared to Hz. Then we will call as EH modes. Okay. Sometimes these are called as E waves, sometimes they are called as H waves. As I said, the notation keeps on changing. So in the next module, we are going to solve these modes in the fiber by following the steps which I have just given you. Step 1, step 2, step 3 and step 4. So we will look at the solutions in the next module. Thank you very much.